I can remind you to record.
Okay. Recording.
If somebody would like to name themselves designated participation viewer who will check the waiting room, be our guest.
I think only I can check the waiting room, but
Oh,
I'll be mindful of that. Okay, so let's first start off with one-dimensional kinematics, right? So then we're starting off at a place where we don't need to use vectors that much because there's only a forward direction and a backwards direction. So anything's either positive or negative. All right, so to do this, we can first just think of yourself as, you're on a car driving on a one-dimensional road, right? And then you're at some x position, x. And in the car you might drive back and forth, and you might have certain changes in position, certain velocities, acceleration. All right. So first of all, just before we hop into any formal definitions, what do you guys think a velocity is? Just from doing math or like something from your daily lives, like displacement over time. Yeah, okay, so then what is displacement? Pooping? Sorry. A vector. All right, so yeah, so displacement is a vector, final position minus initial position. Good. So then you guys seem to have like somewhat of an understanding. So you can have some final, so we can plot our position as a function of time, right? So then at time, like at 1 second, you might be at 1 meter. And then at 2 seconds, you might be at like 5 meters, right? That means you traveled somewhere in the middle. So then we can plot our x position as a function of time. So, maybe we start at position x equals to 0, and then we go somewhat like um, that. All right, so let's just say this is the x position of our car at every instant in time. So then the velocity of the car is just going to be the change in position, some x of t2 minus x of t1, all over the change in time. So it's just going to be t2 minus t1. And for now, let's just assume that we're going forwards in time, right? So then t2 is going to be greater than t1, which means that, in our graph of, okay, yeah, that's going to be our speed, not the velocity itself. Actually, no, it is going to be the velocity itself because x of t2 minus x of t1 can be negative. So I'm going to get rid of the absolute value signs there. So which means that between t2, between some t1 and t2, our car kind of like moved a little bit. So to sort of, and this is going to be slope, right? Because you guys should know that slope is just y2 minus y1 over x2 minus x1. It's the change in y over the change in x. But in this case, our function is x of t, and then the x-axis is t. So then we can kind of draw like a slope kind of thing here. Right. All right. So then this is going to be our slope. But let me just ask you, do you think this is an accurate representation of how fast the car is going over the course of this entire time period? Like, sure, we can say that the average velocity throughout this entire course is going to be this value, right? X of t2 minus x of t1 over t2 minus t1. But yeah, that's going to be our average. But then is that an accurate representation? Because the car, oh, there's more people. It's the line of, it's not really best fit. That's more of like a statistics thing, right? But like,
Hello.
so hello. So let's just say like T1 to T2, this is like the course of an hour, right? So is your speedometer on your car going to be showing this same value over the course of an hour when when your x position is changing like this over the course of T?
No.
No. So then what is it going to show? if not that?
Something similar, like plus and minus.
Yeah, it's gonna take some shorter, it's gonna take some shorter period of time, right? T2 minus T1. So then I'm gonna switch the page. So for more accuracy, we don't want the average.
Arib, yes. So just as a note here, exactly. A speedometer, this is why a speedometer doesn't change exactly as you speed up or slow down. What's going to change is the gauge. The gauge is going to like move. But if your speedometer is just like a number, you're going to notice that when you're moving, it's going to slowly decrease. It's not going to decrease instantaneously. So yes, what the car is doing, it's taking very small intervals and checking checking the change in your position, or how many wheel rotations has gone through, because a wheel rotation corresponds to some sort of length covered on the road. So it'll take some sort of number of wheel rotations divided by some sort of small interval of time and give you some sort of approximation of your current speed.
All right. So yeah, we want accuracy. So we don't just want the average over like an hour, right? We want to have some smaller interval of time for which this exists. So then, instead of having a large T2 minus T1, we want precision. Yeah, okay. We want a smaller T2 minus T1, right? So like what we want is maybe, the T2 minus T1 of like 0.1 seconds or 0.001 seconds, right? And this is T1, T2. So T2 minus T1 is small.
Let's zoom in on it.
Yeah, so now let's zoom in on this specific portion of the graph. All right, so it's gonna look something like that.
Okay.
And T1, T2 is really close together. Now, when we zoom in on a graph, like given any curve, it's sort of like physical intuition that the graph, as the more you zoom in, the less the curvature, the less curvy the graph is basically. And then like when you zoom in enough, any curve basically just becomes a line. So like, does everyone sort of understand where I'm coming from with this? Does anyone like, so give me like a
Someone
thumbs
named
up.
themselves Alvin Lee, or is that just you?
I'm
No,
Elvin.
that's just Andrew messing around. Not Andrew Binder, Andrew Drong.
Ah, I see.
Okay.
Okay.
So like give me like a thumbs up if you sort of understand this intuition.
So here, I can write it out on the board in red markers. So the more you zoom in, or if it actually lets me read, lets me write, the more you zoom in, on the graph of a curve, the straighter it is. There's our little proposition.
All right. So so like let's just say we didn't have a curve, right? Let's just say we had a straight line for our x of t versus t graph. So if we had a straight line, right? And the position is just increasing linearly with time, then it's pretty easy to find the velocity, right? And like pretty easy to find the exact velocity, because what we can do is just we can take x2 minus x1 over t2 minus t1, and this is representative of the slope at every single part on the graph, right? And then, it's just a line, so it's just pretty simple. But if we go back to our curve, we can't have a line approximate a graph really well. So I just got a black screen. Are you seeing this okay?
Ariba, maybe. Oh, they sent a photo. Guys, let's try to keep the chat like to a minimum.
Yes, please. All right, where was I? Right, so if you had a line representing the x to t relationship, then the slope is representative of the slope everywhere. But if you have a curve, then you have to kind of have the zooming in thing to actually find what the instantaneous velocity is at that point, right? Which is why we can say that, when we actually do the process of zooming in, then we can say that delta x over delta t, we want to make t small, right? So as delta t goes to 0, as delta t goes to 0, delta x over delta t. Okay, so by the way, delta x is a way of saying x final minus x initial, right? So it's just a difference of two x's. So delta x over delta t becomes closer and closer to the actual instantaneous velocity at that moment. And in the process of making delta t infinitesimally small, we can notate delta x over delta t as dx dt. Right? And then this is something in calculus we call a derivative. And if you want a more rigorous definition of a derivative, I suggest checking out the math reference sheet we've sent out earlier. Yeah, so then we have this notion of a derivative, which is the instantaneous change in x over the instantaneous change in t. We learned this today. Look at that. All right. And basically what we want to do with our original graph is we want to split it up into portions, right? Where the delta t is as small as possible. So, we can maybe have like a delta t over here, 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 here.
Point is, you're getting more and more precise on what's going on, because what happens is when we talk about average rate of change, when we talk about that, we're talking about the rate of change or the slope of a line that covers this interval. So we're looking at an interval here. We're looking at basically this. But what we're trying to do is we're trying to understand the behavior of this graph or the behavior of this line at a single point. So that's where we get instantaneous from. Instantaneous means at that instant, how fast is the object going? Like not between 0.0003 and 0.0005 seconds, how fast is the object going? Or like what's going on? But how fast is the object going at exactly t equals 0.003 seconds is what's going on. So we're looking here, we have a secant line because it crosses in 2 points. But here we have a tangent line, and it does not want me to write anymore. Here, tangent line. Here we have a tangent line. So if we write out, Alvin, can you make a new page?
Yes.
If we write out what we have, let's see, if we have our function y equals f of x, then our average rate of change is going to be f of x plus some sort of delta x minus f of our x initial over this delta x. Now,
Well,
for simplicity,
in this case, it would be t, right? So then we're really dealing with
I'm sorry, plus delta t, my bad.
The
over f of x over delta t.
velocity is equal to some x of t plus delta t minus x of t over delta t, right? And
Yeah,
this is
sorry, x plus delta
exactly
t.
what we have here. Oh, so we take our original definition for average velocity, and then we just make this thing really small, and we get what we want.
We send it basically to 0. So what happens, what that means is we take a limit. Oh, oops.
Oh.
We take a limit All right, let's try this again. We take a limit as delta t, which is t2 minus t1, approaches 0 of x of some sort of point, x plus delta t, or sorry, x t plus delta t, minus x of t over delta t, which is just equal to dx over dt. There's our derivative. There's our instantaneous rate of change.
Yeah.
I am absolutely not using dot notation. But basically, we should make a note about notation though. There are 3 different types of notation that are typically used. There's Newton notation, there's Leibniz notation, and there's Lagrange notation. So Newton notation is what Arib has talked about. Sometimes you might see something like x dot. This refers to dx over dt. This refers to the first time derivative with respect to x. The first time derivative of x. Same way that this refers to the second time derivative. We almost never use these in regular mechanics. Like you use this in more like college physics. In college physics, you'll see dot. Leibniz notation is d over dx. This is like what you'll commonly, d over dx is like what Leibniz notation does. So dy over dx is the derivative of y with respect to x. And Lagrange notation is primes. So x prime is the first derivative of x with respect to the first derivative of x. So those are the 3 different notations. I have no idea what Euler notation is, but this is, I think you mean Lagrange, whatever. Point is, whatever. So
All right.
in regular mechanics, we only care about usually the first derivative and the second derivative. Nothing past the second derivative is something that matters to us. Now, the second derivative is just the derivative of the first derivative. So if I take d over dx of some sort of f of x, and then I take a d over dx of that, there's my second derivative. Otherwise known as d squared f over dx squared. That's it. That is literally all you need to know about what a derivative is. We can go through some rules. Alvin, do you want to like describe the rules, or should we just leave it with the math sheet?
We should hold off on that for now.
Okay. So right now, we're just going to assume that, you guys either know the rules or will read the rules. We're just going to like take them as given when we derive the kinematic equations. We're going to try to derive them using derivatives, because we've described derivatives.
Yeah.
Again, yeah, these are all the rules and the derivation of the rules are going to be available or are already available in the math review sheet in the last section. And if you guys, by popular demand, would like to see my personal calculus reference sheet, I will send you my personal calculus reference sheet on derivatives, which is about 6 pages. But yeah, now we understand that. We understand like how to map velocity.
Yeah. So basically, to sum it all up, the point of taking the derivative is basically just to look at the slope of a small line, so we have a more exact velocity, rather than taking the slope of the big line, which gives us a very bad representation, a very inaccurate representation of the velocity. So yeah, and then it approaches a tangent line, as Andrew said. All right. So with that being said, I also want to look at the reverse direction. So let's just say that a person with a constant velocity, right? Let's just say a person's always traveling at 5 meters per second. And, so a person has constant velocity and he travels for a certain amount of time, right? So a person with velocity v travels for some amount of time t. So how far does this person travel in this amount of time? Just, by
VT.
yeah, someone said VT, that's right. So then
So
let's just say, like, if I were walking for 5, am I writing in hieroglyphics? It's not that bad, is it? So
would you like me to write?
no, I think I'll be fine. So if I were going at 5 meters per second, right, and then I walked for 10 seconds, then you just multiply that by 10 seconds, and then you get that I traveled a total distance of 50 meters. All right, so what's really going on here is we can graph our velocity in terms of time, right? And then in this case, our velocity is always going to be constant, so it's going to be a straight line. So this is going to be 5 meters per second. Are you doing that? Yeah, we are. So this is going to be 5 meters per second, and then I stop at 10 seconds. So this is 10 seconds. So what's really happening is we're taking the area of this rectangle, right? We're taking 5 meters per second times 10 seconds. This is the area of the rectangle, and we get 50 meters. But now you may ask, what is going to happen if my velocity is not constant, right? So what if instead my velocity with respect to time is equal to like some curvy function? Right? What if it's something like that? Well, you see here, we can also make the same type of rectangle because we before, when we zoomed in on our graph, right? The more you zoom in on a curve, the straighter it is. So, we can sort of split this graph up into a bunch of very small rectangles where, if you zoom in enough on a certain part, it's going to be straight, right? So then we can make it into, like, I'm going to make them big just for the sake of reference, but then, we can, when we're actually making the calculation, these turn into really small boxes. So basically, what we can say is that within this small interval of time, right, because we want to shrink the time in order to make the velocity pretty much flat, we can say that it goes at some velocity for some short amount of time. And we can make the same multiplication of velocity times time equal to displacement, right? So then I'm going to make a new page for this. What's really going on here is we make our rectangles. We're still taking v of, so then let's split them up into like very small intervals, right? So t1, t2, all the way up to t of n here. And the distance traveled, is equal to this v1, which is pretty much flat, v1 times t1. And then now we look at this one, right? Plus v2 times t2 plus,
well, v2 times t2 minus t1.
oh yeah, that's right.
So let's just call this delta t.
Yeah, sorry about that. So then we can assume that the distance between like t sub k plus 1 minus t sub k, this is equal to delta t, right? Where delta t is very, very small, so that the velocity within the time period is pretty much equal, is pretty much constant. Yeah, so then basically we want to sum all of these up to get the total distance that we traveled.
Okay, Arib, we're not going to be doing Lebesgue integrals. in physics.
Please keep the chat relevant. All right, so we're basically, to get the distance, we're taking a bunch of these simple rectangles that we had for calculating constant velocity by approximating velocity to be constant within a small period of time. And then, we finally get the sum from 1 to n of v sub I delta t, which is, so if you wanted to assume the velocity to be constant at any given time, right? You want to assume it to be somewhat like close to where that function actually is. So then, so v sub I, so the v at t sub k is going to be equal to, well, v at t sub k, right? And then that's where we draw our line for velocity. And this is something in calculus known as Riemann sum, which is a way of approximating something called an integral. So as we let delta t approach 0, as we did with our derivative as well, then we can call the sum from I is equal to 1 to n of v sub I, or we should rather say v of t sub I times delta t. We can call that the integral.
Well, as n goes to infinity.
Yeah,
right?
so as n goes to infinity.
So we go the limit as n approaches infinity.
I already have
Of-
it.
Okay, cool.
Infinity, not 0.
Is then the integral of
We
v of
just
t.
call it the integral of v of t. Oh my god, we're very calibrated. V of
Calvin?
t dt from 0 to our final t. Okay, and this is also, so as the rectangles get smaller and smaller, and we partition this t into more parts, making each delta t smaller, we approach the area that's under this graph, right? The smooth area, not the rectangular bulky area. We just approach the area under this graph.
And there are different types of approximations depending on where you set this rectangle to start. You can either set it to start from the left or you could touch from the right. Those are then different approximations. There's a right-hand approximation, there's a left-hand approximation, there's a trapezoidal approximation. The point is they're all just random different types of Riemann sums. Just in general, as we decrease the size of this interval and we increase the number of partitions to infinity, we basically are going to end up with a lot of lines that will all add up to this area. So what's important to note is that there are two different types of integrals. There's a definite integral and an indefinite integral. What we just calculated is what's called a definite integral. A definite integral is a number. It is an area. The definite integral is defined by the integral from one interval of this function. And then we're just gonna, and this gives us an area. This gives us a number. An indefinite integral is something like this, which is gonna be a function. In the same way that the derivative of a function is a function, but the derivative at a point of a function is a number. Like your speedometer doesn't tell you you're traveling x squared plus 3 miles an hour. It gives you a number. So in physics, that number corresponds to your velocity, which is mapped by the function represented by the derivative of the function. In the same way that this area is a number, which is like the total distance in meters that you've traveled, which is defined and modeled by a function given by the indefinite integral. I hope that makes like some kind of sense.
All right. So, in the last couple of slides, we basically said that derivative or the tangent slope of x of t is the velocity, and the integral or the area under v of t is the distance traveled. So does anyone have any questions thus far? Or any points of confusion? Because this is
Type an
some
F in the chat if there's something wrong.
F. Because this is some pretty dense stuff. So if you want some more rigor, perhaps, or like a more in-depth explanation, you should go refer to the reference sheet that we posted. Perhaps take a calc class. Yeah, you'll know the proofs for these in calc.
Yeah. Or you'll know the proofs if you read my reference sheet. Just as a little side note, the Riemann integral defines these intervals. What Arib said, a Lebesgue integral defines the Lebesgue measures. You guys are going to learn about those in like not high school.
All right.
So there you go.
So so in the same way that velocity is the tangent slope of position, delta x over delta t, as delta t goes to 0, or dx dt. We can also define acceleration as a change in velocity. All right, so this is instead dv dt. So if I am traveling at 1 meters per second, and 4 seconds later, I'm traveling at a speed of 5 meters per second. That means I sped up. And if the acceleration was constant, then I would have sped up at 1 meter per second, right? So then I really said delta v over dt. So we can also say that this is delta v over delta t as delta t approaches 0, in the same way that we said v is delta x over delta t, or dv dt. And in the same manner as well, we can say that the change in velocity is equal to the integral of acceleration dt. So, we have like sort of this thing with x, v, and a. Right, so to get from x to v, we take the integral, we take the derivative, sorry. And then to get from v to a, you also take the derivative. Now for the other direction, if you want to get from a to v, you take the integral of a dt. And if you want to get from v to x, you take the integral of v dt. All right. All right. So does anyone have any questions? So we can sort of see from here that taking the integral and taking the derivative are sort of inverses of each other. No, we don't need to know any advanced calc rules, Mr.
So yeah, that's called the fundamental theorem of calculus. That integration is anti-differentiation.
Yeah, so like I said, this is pretty dense material. So does anyone have any questions at all?
Don't worry, we're getting to the physics. Do you need to know L'Hopital's rule? No, you do not. L'Hopital's rule is for limits of indeterminate forms, which is not something you will ever see in physics. Because how the hell do you model something by an indeterminate form? Whatever.
In high school, anyways.
There are two parts to the fundamental theorem, but only part one is important to physics for now. And also as a note, acceleration is going to be treated as a constant for most of mechanics.
Yeah.
So that acceleration is modeled as a constant. And so then from there, we can build out our kinematic equations. Kinematics equations.
Oh my God. Yeah, so now we can, oh boy.
Okay.
So now we can actually, with these definitions in mind, right? So v equals to dx dt a equals to dv dt. X is x equal to integral of v dt, and delta v is equal to integral of a dt. So with these definitions in mind, we can actually start deriving some of these kinematic equations. So firstly, before we get started with these, all of these equations assume that acceleration is constant, right? Which means over the course of time, the acceleration doesn't change. It's just constant, right? Okay, so let's look at a VT graph of some object moving with constant acceleration. So in a constant acceleration, do you think V is going to be linear, quadratic, or cubic, or like what degree of t is V going to be in? Linear? Yeah, that's correct. So then velocity is going to increase. It's not going to be flat. Flat is if acceleration is 0, which means V does not change, right? So then we defined A to be the change in V over time. So then if acceleration is linear, then that means the velocity changes a constant amount every like unit of time, right? So then it's going to be a line. All right. So let's just take this to be, let's take this to be T2, and let's take this to be T1. And this is going to be our V1, and this is going to be our V2. So what do you guys know about point slope?
Oh.
Form.
Yeah, point slope. Okay, so like given a point and a slope, like you should be able to determine the equation of the line, right? So then here's the question. Given V1 at T1 and a time T2, what is V2 at T2? All right, yeah, so this is point slope, which basically says, if you plug in x1, y1 as a point, actually you do need it in a couple of cases. So given a point x1, y1 on a line, like you can pretty much tell what the formula of the line is by using this equation. Y minus y1 equals to mx minus x1. So now let's apply this. Right, so we know our y1 is v1. Y minus, we want to find the equation of the line. So y minus v1 is equal to, and what is the slope? What is the slope of the line? A. Yeah, that's right. So it's changing at a rate of A, right? And that's going to be the slope. So it's going to be A times x minus x1. And now we know what our x's are, right? The x's are actually t's because that's what we have on our axis. So it's going to be t minus t1. All right, so, and we also know that we're given a time t2, right? So this means this is just t2 minus t1. Okay, so now let's expand that. So y minus v1 equals to 8t2 minus, and we're just gonna call t2 minus t1 delta t as well, because that is our change in time, right? A delta t. And then let's add v1 on both sides. Y equals to a delta, I'm gonna put the v1 in the front. V1 plus a delta t. All right, and what is y? What is the y that we found? Anyone? So what is on the y-axis? Yeah, it's going to be v2. I'm going to finish it off. So v2 is equal to v1 plus a delta t. And this is our first kinematic equation, which sort of makes sense because, you know, if you're accelerating and the new velocity that you're going to be at is going to be equal to your acceleration times the amount of time you spent accelerating. Can you just derive that from the acceleration formula? Yeah, you also can. Like, okay, so
You integrate.
Here's what Benny's talking about.
That's Andrew.
So
He renamed himself.
A is equal
he's doing
to
the wrong
a v2 minus v1 over t2 minus t1 equals to delta. All right, and then so A times delta t is equal to v2 minus v1, and v2 is equal to v1 plus a delta t. Okay, yeah, good. That's a good alternate derivation of that fact as well. And yeah, you can also use calculus directly because we know that, yeah, we can just take the integral of acceleration and we get v times t plus v sub 0. Okay, so this is the first of our kinematic equations. Any questions on that so far? Okay, so
Yeah, it should be AT, right? Not VT.
Oh, sorry. Yeah, my bad. AT. Yep. Sorry. My mistake. V equals 8 is AT. Yep. Thank you. So V T equals this equals AT plus V naught. And I just want to make a note. The reason we add this, like, so as you will learn either from the reference sheet or just common sense, the derivative of a constant is 0. So if I have like f of x plus some sort of constant c, the derivative of this is just going to be this, and the constant disappears, which means that for any c that's real, the derivative of this is going to be just this, which means an infinite number of possible functions will all have this same derivative. The problem is, if you try to reverse this and go back to this, because all of the c's went away, you have no idea what initial c you started with, which is why whenever you integrate something like this, you're going to have f of x plus some sort of constant, because you have no idea what that constant was, because this constant can be anything. So this is where we get this constant, because, you know, the assumption is, in some cases, if you were moving, yeah, exactly, the y-intercept of a line can be anything, and the slope would be the same. So if I have like one line where the y-intercept is here and another line where the y-intercept is here, the slopes are exactly the same, but this area is different. So v naught represents that y-intercept, that initial velocity. In a lot of cases, it might just be 0, but for our kinematic equations, we always use that v naught, or in Alvin's case, v1. We always start with, you know, whatever speed you were moving at initially, and then plus at. So that's just a note on why we have that v naught in the calculus derivation. That's where it comes from. In the algebra derivation, you could just see it. It just comes from, you know, average rate of change. Here, it comes from that constant.
all right. So let's continue. So the first thing we had was v2 equals to v1, v2 equals to v1 plus a delta t. Right. Okay. So now what I want to do is I want to derive another kinematic equation by taking the derivative of the first one. Right. I mean, taking the integral of the first one. So if we take the integral of the left and right sides with respect to time, then what are we left with? So integral of v2 dt is equal to the integral of v1 dt plus the integral of a times delta t, which I'm just going to call t for now, dt. And there's something called the power rule, which is basically if I take the integral of any like constant times x to the n dx, then it's going to be equal to x times x to the n plus 1 times 1 over n plus 1. All right, so we're going to be using this. So first of all, we have v2, integral of v2 dt. So then I'm going to call that, like, this is the distance that we covered, right? So this is going to be, you can do it with limits, I think. Perhaps, but this is the derivation we're going with for now. So we have the distance covered, which we're going to call s, right? I don't know why, but displacement is called s. So s is going to be, we're not going to put a vector on it for now. S is going to be equal to, so the integral of v1 dt. Now v1 is the velocity that we started with, right? So that's actually going to be a constant. So it's going to be just v1 times t, because if we take the integral of v1 times t to the 0, basically, dt, this is going to be by our rule, t to the first times v1 over 1, right? And this is just equal to v1t. So v1t plus the integral of at dt. And then this is going to be a times t squared, but then you have to multiply that by 1/2 from our rule right here, which is called power rule, by the way. Now, this is the power rule of integration. And with that, we actually get our second kinematic equation, which is the displacement is equal to the initial velocity. I'm just going to call that v0 actually. The initial velocity, v0t, plus half times the acceleration times time squared. Can you derive from the graph as well? Yes, you actually can. But you're going to have to, if you wanted to start with constant acceleration, then you would have to get that velocity is quadratic. And then you're going to have to find the area under a quadratic graph, which is, actually, no, you're going to have to find the area under a linear graph. But yeah, this is basically what it is. And if you want a linear, if you want a graphical interpretation, right? So if this is our acceleration, so acceleration is constant. So, you know, we have velocity with respect to time, and this like increases linearly, right? So like that. And then we want to find the distance traveled. So this is t. So this is going to be our delta t. This is v0, and this is v1. Right. So then v0t. What is v0t? V0t is going to be this rectangle, right? Because we want to look at the area under the VT graph to find the distance traveled. This rectangle is going to be V0 times t. And then we look at this triangle, which is the acceleration, right? Acceleration times time squared. So this is delta t again. And this is going to be delta t times the slope. So we add on the area of half times delta t, which is, I'm just going to call t, times t times a, and this is equal to v0t plus half at squared, which is the same formula again. I think everyone's staring at you.
He's joking about the classroom profile. Let's try to like. Yeah, that's a background. Yes, he's not actually at Sty, and they haven't been motionless for the last 45 minutes. That's a photo. By the way, yeah, they use S for displacement because it stands for the Latin spatium, which means distance covered.
Right. So yeah, this is our second kinematic equation. And now let's move on to the third. All right, so in the case of constant acceleration, we can actually just say that the distance traveled is equal to the current velocity plus the initial velocity all over 2 times t. And the reason for that is because assuming linear motion, right? This is the same thing as if we have delta t. So this is v0, and this is v1. This is our current velocity, right? So it's the same. Taking the area of this trapezoid is the same thing as taking the midpoint of v0 and v1, which is over here, v0 plus v over 2. And, just making a rectangle, right? Because if you have trapezoid, you take the midpoint and then you make a rectangle out of it, then you're basically moving triangle number 1 to the position of triangle number 2, right? So then it's the same as, just having this rectangle instead of, doing the other formula. However, that other formula is useful, but this is kind of a shortcut for if you don't have time, if you don't have if you're not given the acceleration, rather, you can just do this. All right, so now what we can do is we can say that acceleration is equal to v2 minus, Andrew, what is that?
That was my pen spasming for literally no reason.
v2 minus v1 over t. So then that means if you take the acceleration times the distance, this is equal to half times v, or v2 plus v1 over 2 times t. So that's that's what we have for distance, and then multiply it by acceleration, right? Which is v2 minus v1 over t. And certain things cancel out. This cancels out with that, and yeah, this cancels out with that, and
Are we deriving?
oh yeah, I
V?
I put 1/2 twice, so this shouldn't be there. So v1 plus v2 over 2 times t times v2 minus v1, and the t's cancel out. So on top, we're left with a nice difference of squares. v2 plus v1 times v2 minus v1 is equal to v2 squared minus v1 squared, right? And the bottom, we just have 2. And this is equal to the acceleration times the displacement. And just like that, we have our third kinematic equation. Does anyone have any questions so far?
Also, just equivalently. You might see this.
Yeah, and then, you can sort of mess around with the formula, rearrange the furniture. That doesn't really quite matter. But, there's
Yeah. Just in terms of notation, you might see it like that. What else? Those are the kinematic equations. Anybody have any questions about any of our derivations, any of the formulas, any of the concepts? F in chat if you have a question, or just yell it out.
Wait, so there were 2 ways to represent displacement, right?
yeah. So I'm
And,
going to write out what we have derived so far.
So the original one with the t squared, that would be like when your velocity is not constant, right?
Uh, yes,
That's
that would be correct. Like, so v is equal to v0 plus at. The second one, s is equal to v plus v0 over 2 times t. The third is s is equal to s0, or I'm just going to use x, actually. So x is equal to x0 plus, no, delta x. The distance you travel is equal to v0t plus half.
No, it is x0 plus v0t plus 1 half at squared, because when you take a double integral, you're going to have the c from this integral and then the c from this integral.
Yeah, but I'm just using delta x.
Okay.
And then the fourth is v2 squared minus v1 squared is equal to 2 times the acceleration times the distance traveled. All right, any questions so far?
So this is our vt function. This is our vx. This is our, excuse me. This is our, I don't know how to say it, average rate of change. This is our xt, and this is our vx.
All right, any questions at all? We covered a lot of ground.
Where do we need to solve for time? Where's the fifth one? There is no fifth one. What do you mean?
All right, so on that note, let's take a 10-minute break. So we will see you at 5:42.
Yeah, 5:42. And obviously, if you have any questions, you can stick around and ask them. And if anybody wants to hear a fun calculus problem, feel free to stay. Let's pause the recording though. On deriving the kinematic equations. Point is, just know, believe us, we have derived them. Here they are. And now we can try to apply them to a practice problem. And then we'll talk about projectile motion.
All right, I think most people are here. All right, so I guess we can do a practice problem. All right.
Today's Tuesday, right?
Today is Tuesday, which is why we're here.
It's going to be a slow week. All right.
All right.
Yeah, that's why I asked Jeremy. Okay, so let's do a practice problem.
So, all right, let's just say a car. So a car drives, a car has an initial velocity of, 5 meters per second and accelerates at 2 meters per second squared, which is 2 meters per second for How long do you, give me a number? Anyone?
20.
Let's go with 10.
Oh,
All right. For 10 seconds. And then the car also travels at the final velocity for another 10 seconds. So find the displacement. So I'll give you guys, a couple minutes to do that. And you should send me or Andrew an answer in private Zoom messages. All right. Since these numbers are random, I have to do it myself as well.
let's see.
Yeah, Ivan looks good. Looks good, Mohammed.
Just give another minute for people to send in.
Ooh, Steven, I would check my work. Or you should check your work. Jeremy, you're a little bit off. Let's give until 5:50 for answers. Yeah, by the way, resubmit if you didn't get the right answer.
Did you start? Oh, yeah, you did. Okay, cool.
Pretend I used 2 for the, I don't know what you're talking about. You gave me one number. Yep, looks good. Steven, you're getting closer. Two, 3, 5, 2. I don't think that's right. 7.
People who are getting weird answers. You
That
guys
should
might be
a
overthinking it.
really nice answer.
Wait,
Be like a
it's
very
supposed to be
clean
really
answer.
nice answer. No radicals.
No
No
radical.
radicals. How would you even get radicals? You'd have to have like a fourth root somewhere to get a radical.
This is a very nice number. $322. That's not right either. Can I just not multiply? My grandma is this age. All right. Let's not go there. Okay, so who wants to present their solution? out of the people who
Well,
Let's go to a new page and like
yeah
just someone start writing.
yeah, Ivan, so go ahead. And you should also like say what you've done while you're writing it.
Okay, so for like the
Or-
first
or read-
part,
read. Hold on, someone else is presenting.
okay, so you have like two parts, and there's like the first part, which is like the arc thing. So you use the s equals initial plus final times time, which is 10, and then that's like what, which is 150,
Yep.
and then in the second part, it's just traveling at 25 for 10 seconds. So you just multiply, and then you add them together to get total displacement. Is 400 meters.
Yeah, that is a very good solution. So did anyone, does everyone understand the solution? Any questions? Or, did anyone do it differently? I'm gonna rewrite some of this because this is a little bit messy. So he's saying here that S, which is the displacement, this is supposed to be a 2, right? So then, and this is a 25. Okay, so how did you get 25?
Because the final velocity is equal to, using the first equation.
Yeah,
Yes.
so VI plus AT, and this is equal to, so VI is equal to 5, and 5 plus 2, 5 plus 2 times 10 is equal to 25. And this is where the 25 comes from. And then he used S equals to VI plus VF over 2 multiplied by time. So which he got 150. And finally, it's just driving at 25 for 10. So that's 250, and you add them and you get 400. Great. So we can move on. So do you think
I have a actually. Oh, sorry. Go ahead.
do you think we should do another problem, or do you have another good problem, or
I have one.
all right,
Yes.
go ahead.
Sorry. So a person's traveling at 15 meters per second east after accelerating for 25 seconds at for 7 seconds.
Right.
After accelerating for 25 seconds at 3 meters per second squared west, how far is the person from where they initially started?
Yeah, so take a couple minutes to do this one and private message us the answer that you got. Let me just Wolfram this ugly expression.
Okay, this one's a little bit longer, so it's okay if you guys don't get it yet immediately. Also, the numbers aren't going to be as nice. I apologize in advance.
Okay, I have many different answers, and
So does somebody want to try to present an answer?
okay, yeah, no, Steven got it correct, actually. Otherwise, I don't think any of these are right. Check your work.
Okay,
I think we
is
should
this...
a little bit more time, until like 5 or 6 o'clock.
Yeah, pick
Wait,
some time and then we'll write it out.
wait, Steven, the only issue with yours is that it's just how far the person is, right? So take the absolute value. But otherwise, I think your answer is good. That does not look.
Alvin, I would check that answer.
Really?
I'm pretty sure. Let me... Oh, actually... Oh, no, my bad. Sorry. Let me see.
The one I sent to you is right here.
Let me just check. um,
Ooh.
let me see.
Is the car moving?
Car. There's no car.
There's a person that's moving irrationally fast. I don't think that is right either. Yeah, I see another correct answer, Arib. Yeah, Arib, that looks
Let me
right.
see this.
Yeah, guys, remember to add 15 times 7 because that's the part he moves without accelerating. Does he start walking in reverse? Yeah, he does.
Well, kind of.
All right. So out of the people that got it correct, it's really like the same thing as the last problem, except now it's like the other direction. So who wants to present?
Can I go?
Who's that? Steven, right?
Yeah.
All right, sure. Go ahead.
Okay, wait, can you get a new page? Or...
Is this enough to write, or do you want a new page?
Oh wait, yeah, I think that's enough.
All right.
So
Just draw a line here.
let me see what I did. Okay, so you know the first part, he's moving at 15. It's a constant velocity, 15 meters east, 15 meters east per second. Oops. Okay. And then you want to multiply that by 7. So that's your that's how much distance he has moved eastwards. So you want to multiply that. Oh my god. Okay. And that would give you, I believe, 7, 105. This is positive, and then you want to find the second part, and so the acceleration was 3 meters per second, 3 meters over second squared, and then you multiply that by 25 seconds, and also 3 is negative because you're moving in a west direction, and you want to add that to your initial velocity, which was 15 meters per second, right? And that would give you, I believe, negative, what was it, negative 45 meters per second.
And then you want to find the total displacement for moving west. So that would be negative 45 meters per
Wait,
second.
isn't that negative 75 plus 15 is 60?
Oh. Oh yeah, my bad. 45 would be your the other number. Hold up. Okay. Yeah. My bad. Okay. And then wait. No, it is 45. What?
I think it's
Wait.
60. Yeah.
Oh yeah, my bad. Okay. And then you yeah, I see. Okay. And this 45 you got from is it the initial velocity plus the new velocity, which was negative 60. Sorry. Okay. And then you want to multiply that by your total time, right? And then you take that as value and you would just add it. So it was negative, what is it, 105 meters plus, that's a 2. Okay. Sorry, this is a little messy. And that would give you negative 457.5. And because it's asking just for the magnitude, because you're asking just for the distance, it would just be positive 457.5.
Yeah, very good.
Sorry.
So, meters, and maybe since it's negative, it would be, I guess it would be helpful to write west, but that's not really something you have to worry about. So 457.5. Any questions? Yeah, it's basically the same thing as the last problem, where yeah, this is where the solution was, where you find S and there's no adding in this case, but then actually, yeah, there is adding. So in the first problem, there was the person walked some distance in the beginning, and then here it's the same thing. So some person walks some distance in the beginning, and then you find how much it traveled while it was accelerating, and then you add these two, and then you get 457.5. Okay, so I guess now what we can do is, well, we can apply what we know about the kinematic equations to a real life sort of example with free fall. Right, so free fall is just when you drop something with some height, at some height. So for example, let's just say that I am on the top of a cliff and this is me, and then I drop a baseball off the cliff. Right, so what is causing the baseball to like fall to the ground? What is causing the baseball to fall to the ground? Yeah, gravity, right? So it just so happens that like on the surface of the Earth, gravity is always going to cause a constant downwards acceleration. What is 1.8? I don't know. And the amount that gravity accelerates an objects towards the ground is actually going to be a specific numerical value of small g, which is what we call it. Small g is equal to 9.8 meters per second square downwards, right? But then because we're physicist engineers and we like to approximate, we can just use g equals to 10 meters per second squared. All right,
Which is
so
obviously equal to pi squared. Duh.
yeah, which is obviously equal to pi squared. All right. So yeah, and then you can use the same equations that we use for horizontal motion, except it's vertical now, right? So there's always an acceleration equal to 9.8 or 10 meters per second squared. Okay, so I guess I can give you guys a quick problem. So let's just say that, okay, so problem. I drop a baseball from a height of 200 meters with the initial velocity is equal to 0. So which means I just dropped it. I did not, give some sort of velocity to the ball like before. I didn't throw it, right? So I just dropped it. So how much time does it take for the ball to hit the ground? Yeah, so take a couple of minutes to do this one. And as usual, PM answers that you got. Yeah, so anyways, in physics, you want to try to give your answer in terms of a decimal as opposed to, yeah, you want to give your answer to a decimal in terms of a decimal as opposed to like square roots and stuff, because like the point of physics is sort of like with significant figures and accuracy, precision and such. You want numbers in like float form. Yeah. I gotta actually plug the thing into Wolfram. Yeah, so these look good so far. These all look good. Let's wait like 2 more minutes for solutions. So Andrew, if you're getting any on your side, just say if they're right or wrong.
I got one from Arib. Let's take a look.
Yep, that looks good, Mohammed. These all look good so far. Is it? Yeah, it is. Okay, so this is like not that bad of a question, so I'm just gonna quickly go over the answer. So we can use negative 200, which is the change in y, is equal to v0t plus half gt squared, right? V0 equals to 0, so this cancels out to 0. And gt squared, okay, so we know that, oops, I didn't need to do that. Okay, so half at squared. And then we know that a is equal to g going in the downwards direction. So a is equal to negative g, which is negative 10. So negative 200 is equal to negative half times 10 times t squared. So negatives cancel, and then this canceled out to 5. And then 200 divided by 5 is equal to 40. That means t is equal to the square root of 40 equals to 2 root 10, which is about 6. All right. Ooh, Jeremy, I checked my work. So yeah, any questions? Yeah, and because of sig figs, the answer is just 6 seconds, because I have one sig fig here, and I guess this is infinitely precise, but that doesn't matter. So just 6 seconds. So for the people who didn't get it, does this make sense? Yes, no, maybe? Questions? Missed a negative sign. Ouch. Okay, so this is actually pretty important because we're going to be applying it to angle launched projectile motion, which is our first delve into two-dimensional kinematics. I have 15 minutes left. That's enough.
We're going to be learning about all the different types of collisions, Arib, just not now.
Yeah. Projectile motion. So what is a projectile? A projectile is basically just, if you have some object on the floor, right? And then you launch it at, so this is yx, right? And then you launch it at some angle to the vertical, right? So let's just call this theta with some starting velocity v0, right? And then this got launched. And over the course of its journey, over its trajectory, which is going to look somewhat like a parabola, right? It's going to get pulled down by gravity, right? So it's going to always have a g acting on it, but then nothing else is going to, there's going to be nothing else acting on it, right? So it's just going to go up sideways and then go down sideways, and it's going to hit the floor. And that's where the projectile motion ends. All right, so now how are we going to deal with projectile motion? So first of all, something we have to notice right away is that the only acceleration that's acting on the object is g, which points downwards. So we can, first of all, we can decompose the initial velocity vector, right, into its x and y components. So this is going to be, so if you remember from our vector lesson, how we can decompose a vector. So this is going to be v0 times the cosine of theta, and this is going to be v0 times sine theta. Right? And then it's going to, so it's going to have some initial velocity upwards and some initial velocity sideways. So first of all, is there anything affecting the sideways velocity at all? Like, is that going to change at all throughout the course of motion? No, sir. And why not? Because we're ignoring, I mean, yeah, okay, so disclaimer, like ignore air friction, right? But that goes for pretty much every high school physics question. Yeah, right, so we're ignoring a bunch of stuff because the horizontal vertical kinematics are different. Well, they're not really different, but like, what is the only acceleration that's happening to this particle as it's going throughout its course of motion? Like, the only acceleration that's happening is downwards, right? And then if you're accelerating downwards, that has nothing to do with your sideways velocity. So which means off the bat, we already know that V0 times the cosine of theta, which is the horizontal component of motion, this stays constant. And this is actually pretty important because it determines like how far this particle is going to go. All right, so what about the vertical component? Is that going to change? So is the vertical component going to change? Or is it just going to continue flying out into space? Hello, anyone? Yeah, it will change. So how will it change?
It's better if I say it because I don't want to type that out.
Yeah,
It's
go ahead.
the equation where it's like the initial height, which is going to be 0 in this case, so you can omit that, and it's v naught in the y direction, the y component of v naught, so v naught sine theta times time plus, well, minus 1/2 gt squared.
Right. So if you only purely think about it on the like yt on like the y-axis, right? What's happening to the particle, what's happening to the height of the particle, it's actually following exactly what we described in just free fall, where you have the thing that's going up, and then because of gravity, it's going to accelerate and it's going to go downwards, right? And that's going to happen until it hits the ground. So because of one of the kinematics equations, like this is what's going to govern the y position of the particle. And now you might notice that for any delta y, there's going to be two values of t that satisfy it, right? Except for one position. And that is because like if we look at the projectile motion graph, like it's gonna have the same y coordinate at exactly 2 points in time. And the first point in time is when it's going up, and the second point in time is when it's going down. So if we solve delta y is equal to v0 sine theta t minus half gt squared, you're going to get like the two instances in time where it's gonna be at the same height. All right. And also, if we set delta y equal to 0, right, which means it's either here or here at the beginning or at the end, if we set delta y equal to 0, then we get 0 is equal to v0 sine theta t minus half gt squared. And using this, we can find out the amount of time it takes for it to complete its entire trajectory. So like here, we can assume that t is not equal to 0, right? Because then that just means it's at the beginning and y equals to 0. That's kind of boring. So we can divide by t on both sides. And we get 0 equals to v0 sine theta times minus half gt. And then we move stuff around, we get half gt is equal to v0 sine theta. And finally, t is equal to 2 v0 sine theta all over g. And this is one of the things we can derive just from looking at our two equations for a parabolic motion, which is t equals to the total time it takes is 2 v0 sine theta over g. Any questions on this so far? No? All right. So I guess there are some other things we can derive as well. So the other two important things we can derive are the range and height of the trajectory. So range is equal to the total horizontal distance traveled. And the height is basically this maximum height that the particle reaches. So just as an exercise before we leave for today, I want you guys to, oh, we're at the 20-page note limit, guys. All right, I'm gonna save this then and make a new board.
And while you're making a new board, I'll make a note of these equations for projectile motion. So given our vertical component here that we computed, we see that the vertical component is proportional to the sine of the angle and g. Therefore, if I throw if I let an object just drop to the ground versus firing it forward, which one will hit the ground first? This one or this one? Okay, so I'm seeing
They hit the ground at the same time because they for both like the vertical motion is they're both equation free.
exactly. The time it takes to hit the ground is then independent of the horizontal component and is only dependent on the vertical component because the angle is 0. And because the angle is 0, then it no longer has any effect on the total time of flight because your sine theta is then just 0. So that's why if you drop a ball like standing still versus throwing it forward, they'll hit the ground at the same time. Now you get why. Because in this case, the motion is independent of the horizontal component. All right, sorry, go ahead. Go ahead, Alvin, back off.
So I'm just gonna clear this. Okay. So I guess as a parting exercise, so yeah, given V0 and theta, find max height and range in terms of V0 and theta. All right. So this wouldn't really be a simple thing to type, would it? I guess it's fine. Just send your answers in chat again.
Or write them out on the board. Like you can write out your derivation because we are running a little short on time, so feel free to collaborate.
Yeah. Is the vertex of the parabola, indeed.
Yes.
But maybe next time we will spend a tiny bit on the equation of the trajectory.
Yes, because the problem is vertex of the parabola gives you no information because usually the vertex of the parabola is defined in terms of the function and in terms of like some points.
Yeah, you can. And then we might do something with that later. Ivan, so half GT. Okay, but you don't know what T is, right?
Oh, Jesus, how did you get a theta in the Zoom chat?
You don't know what T is, right? The only things you're given are V0 and theta. So, I mean, that would be something regarding parametrics.
And the maximum height has nothing to do with the time of flight. Like consider, like whether it's flying for half a second, like a bullet, or if it takes a while, like an airplane, you know, their maximum height might still be the exact same thing. It just depends on its velocity and depend on the angle. It shouldn't depend on the time at all. Assume t.
Yeah, Mohammed, that looks correct. And what about the range?
Which should also be independent of t.
Yeah.
You can use Vy equals 0.
Mm,
Well, Vy is never 0. Vy is constant. Or sorry, not Vy, sorry, Ay is constant. Find critical points. Oh, Jesus. No, you don't you don't need to take derivatives. It's simpler than that. Don't overthink it. Also, I'm not even sure if you can find it using derivatives. Can you? Like you have to set the derivative equal to. Yeah, but then the sine of the angle wouldn't come from anything, and you'd need to know the equation of the parabola. Yeah, but that's the equation of the trajectory, which we haven't discussed yet. So you literally need to know bonus information to be able to do what you want to do.
just by the way, the piece set is due tomorrow. So if you haven't done it yet, please try to uphold the deadline. The piece set, the problem set, R is equal to,
We are a physics team. We don't call it homework. We call it a problem set.
yeah, that looks right, Mohammed.
So Mohammed, you want to give your derivation on the board?
Someone's writing. Who's it?
Oh, someone's writing?
The problem set is in the Google Classroom.
Yes, and we've reduced the problem count from 7 to 5 because I was ridiculously late and the extension doesn't even give you that much extra time. But yes, again, we gave you guys an extension. Please get it done by tomorrow midnight.
Okay, I can't drag and type here. Oh yeah, so I guess if you're new, you can check out the Discord, which is where we're posting a lot of stuff now, and the classroom link is in there. 2 equals.
Can I annotate?
Sure, go ahead.
Wait, hold on. Muhammad is typing in chat. Yeah,
You
but
can
go ahead.
annotate
Both of
what
you.
Um,
Annotate.
That is so loud typing. Let's see. Yes. T equals 2v naught sine theta over g. T over 2 then equals v naught sine theta over g.
And plug in T over 2, and you get half V naught squared sine squared G.
Sine squared theta over g.
Yeah, sine squared theta over G.
He doesn't want to write theta. Or the theta isn't registering.
All right. Sorry, we're holding you a little bit over time. Oh, what happened?
I accidentally cleared it.
All right.
All right, I think we'll just speak it out loud. Actually, no, I'll write it here.
Yeah,
So
so then we have from last slide that T equals to 2V naught sine theta over G, right? So then that means T over 2 is equal to 2 V naught sine theta over G. All right, yeah, go ahead. And then range, plug in T over 2 in terms of for the height, and we get half.
so let's see what we get. We get 2 v naught squared cosine. Did you write cosine of sine of theta?
Cosine times sine, I think.
Theta sine theta, yes. Over g, which means we can simplify this to v naught squared sine 2 theta over g. because we got 2 sine theta cosine theta. And here is our range. Trigonometry can go, I don't know, somewhere.
And then the height, we can just plug in t over 2 in for the vertical motion equation. So vertical motion is delta y is equal to v naught sine theta times t minus half gt squared. And then we plug in t over 2, right? So then delta y is equal to v0 v naught sine theta times v naught sine theta over g minus half times g times, I'm running out of space, v naught sine theta over g squared. I'm gonna go back one. I have this saved, so they're all.
Oh boy.
Okay, I have to copy all this over. V naught sine theta. All right, what did I have? V naught sine theta squared over g minus half g,
FG.
and then the g's cancel, right? So,
Yes.
and then we have again v naught sine theta over v naught sine theta squared. Where'd you get the range from? Okay, so range is basically, right, so then we found the time it takes, right? So then because there's nothing affecting horizontal motion, we just multiply the horizontal velocity by t, right? And then this is why we get 2 v naught sine theta times v naught cosine theta over g, right? And all right, so I am sensing that something went wrong here.
Yes, as is common with our little derivation sessions. Let's see. V naught sine theta squared over, why are we squaring V naught sine theta?
So times t over 2 minus half g, maybe this isn't wrong. And then we have v naught sine theta.
You think some people left. Oh, some people might have had to go at like
Times like 1 over g
6:30
minus 1/2,
times it. We've gone
which is equal to v naught
over.
sine theta squared times, okay, yeah, something went wrong here. Yeah, I guess everyone is, I messed up the derivation. Okay, that's all right. That's all right. So yeah, we'll send out the notes for this and plus the derivation.
What just happened?
You got
Okay, I lost connection, guys. It's all right. So actually, yeah, I think we're done for today. So there's gonna be a piece set on kinematics. There's gonna be a piece set on kinematics